It's my chemistry, and it doesn't really fit me, and I know I'm fat. Okay, we're over that now. All right. So that first one, it's straight off the test. Both of them are actually, and it's multiple choice, and it's for its difficulty level, it's missed way more than it should. Anyone willing to risk it? 4 is false. 2 is the correct answer. So if you didn't have 2, don't think you're stupid, but let's just think about it real fast. Carbon can form 4 total bonds, right? That's single bonds, but each line represents 2 electrons, right? So how many total can it have? 8, which means you can have a double bond on each side, and that would be the maximum amount of double bonds you could have is 2. You okay with that idea? All right. Today we're going to blow things up and say you can have more, but you have to be on row 3 or lower to ever have more than 8 total valence electrons. Carbon is not on row 3 or lower, so we're going to be fine. Okay, this one is just a vocabulary term. Which one is it? Electronegativity. We've barely maybe heard of that. I don't think we even have yet. Electron charge ratio, what is that? Not something we talk about in this class. Diamagnetism, those two are related. And the first ionization potential is something that doesn't even make sense. So it's E. You okay with that? All right, hopefully you're solid. I'm going to pause the video real quick and show you your current grades. All right, so this is just barely where we ended Friday. So you probably didn't get anything out of it, and it was a Friday. So I've just completely restarted the conversation about formal charges. So formal charges are used to determine the best Lewis structure when there is more than one valid Lewis structure. And I drew that example in there. This was the same example from your notes, which was carbon dioxide. All right? So when there are more than one that actually satisfy the other previous rules, which was that the least electronegative was in the middle, that we connected everything with at least one pair, then we octet the outside, then we octet the inside. And both of these models are valid for those rules. All right, but we need to know which one is the best one. So we follow this concept called formal charges. So for each atom, we're going to count the electron in lone pairs and half the electron it shares with other atoms. Okay. I'll pause this for a minute. There's a ton of your writing, and I want you to look. So write what you're going to write, and then in a minute we'll... Okay, so I've added the dots just to help us count. We're going to look at each individual thing, or atom. We're going to follow these rules to figure out what's going on. So our formal charge for each atom, so we'll look at this oxygen right here. There's that double bond right there. So count the electrons in lone pairs. So this one has 1, 2, 3, 4. Are we okay with that so far? All right. And then half of how many it's sharing. If there's a double bond, how many is it sharing? It's sharing 4. And we take half of that, and that's 2, right? So I have 4 plus 6 for this oxygen, which is 4 plus 2 is 6. All right? And I subtract that from the number of valence electrons for that atom. So oxygen's in family 6, so it has 6, right? So 6 minus 6 is just a 0. I'm going to put a little 0 right there. You okay with that? All right? And now, if you notice, this is the same structure, just mirrored. So I don't need to do the math again. It's just 6 minus 6. So I'm going to put a little 0 here on that oxygen. Are we okay with that? It's the same structure or bond. All right, and then carbon, all 8 of its valence electrons are shared, so really it has how many assigned to it? Half of 8, which is 4. Is everyone okay with that? All right, so it has 4. I subtract it from the number of valence electrons, and I get 0, right? Okay, so in this structure, all 3 of them have a formal charge equal to 0. Easy enough so far. Okay, and by the way, that's going to be the one that is correct, but the one on the bottom is also a valid structure, and we'll use this idea of formal charges to figure out why it is not valid. All right, we do the same math. This time I'm counting 1, 2, 3, 4, 5, 6, and then half of this shared pair is 1, right? Okay, so I now have 7 that are assigned. And I subtract that from the number of valence electrons. So I have 6 minus 7, so this is now a -1 for its formal charge. Thumbs up if that made sense to you. No, Agrin? Okay, I feel like sometimes I bully you just by looking at you. I don't mean to. Okay, if you look here, carbon has an octet and it's still sharing all of them, which is what it was above, so that'd be a 0 again. Same math on that one. But this oxygen is definitely different than any oxygen we've done before. It has these 2, correct? So it has 2, and then it's sharing 6, so what's half of that? 3, so I have 5. So I take my number of valence electrons, which is 6, because it lives in family 6, and I subtract the assigned, or this number that we got right here, electrons, and I get a +1. And I put a +1 right here. All right. Looking down here, the best Lewis structure is the one with the fewest charges. Okay, this is what we do. We assign them and then we figure out the best one. Since this one had 0 charges, it's the best Lewis structure. All right, second also works for this model. The best Lewis structure puts a negative charge in the most electronegative atom. If you look here, O is negative right here, and it's just happy as could be right there. But over here, O is positive. And can carbon make oxygen be positive? No. What's the only thing that can make oxygen be positive? Fluorine. It has to be more electronegative than it. So even though this is a valid structure, according to formal charges, this is the real Lewis structure for this molecule. Yes, sirs. No, it certainly can. But if it does, it will be very short-lived. And that pair of electrons will rotate back to the other side. Agrin? Okay. So, yeah, they can, but very rarely. And so what we draw is what the most common Lewis structure for the thing would be. All right, will you give me no fingers if that made sense? 5 fingers if you think it's pretty solid, and anywhere in between. Ready? I need some feedback real fast. 5, 4, you're asleep. That's how good she is. Okay. All right. Well, that's not bad. We probably averaged a 4. And no one gave me the bird, so that's a good sign. All right. So let's look here. Will you try this on your own and then talk through it with your lab partner? Okay, so remember it's valence minus assigned. And the assigned, it was every dot and then half the shared pairs. All right? So all of them are shared, and there's 8 that are shared, right? So there's how many assigned? 4. Nitrogen lives in family 5, so it has 5 valence electrons. So what's my What's my formal charge then? A. Who had A? Raise your hand. Okay. If you didn't have A, hopefully you're all right with that. I got a question. Ask your partner this real fast. Is the formal charge on each oxygen the same? Each oxygen in this picture. Have a short discussion. All right, so was it the same on all of them? No, this is an easy question. Well, it's a quickly answered question. You just look, so all three of them have the same Lewis structure like themselves. No, these two are equal, right? But this one's different. You okay with that? Just quickly, to help us review, 1, 2, 3, 4, 5, 6. So what's the formal charge on this one? That's a 0, because I just cut those in half. 1, 2, 3, 4, 5, 6, 7. So what is it here? -1 and -1. And what did we say nitrogen was? +1. If you'll notice something real fast. What? No. It has 6, then it shares a pair with nitrogen. What's wrong? What am I doing? Well, I don't take it away, I share it. And it comes, okay, I get what you're saying. There's two, I don't actually think I get what you're saying. It's a valid structure though, trust me. How about that? Will you guys notice something? What do these three formal charges add up to? -1. What is that right there? It's a -1 or a 1 negative. What's that? Nice job, Boyd. All right. Now, we have one more example I want you to work through. Assign formal charges to each atom here, if you would. And then can you explain to your partner any weaknesses with this Lewis structure? Ready, set, go. This next chunk, like, you need to know what it is, but we don't need to spend more than 4 total minutes on it. That's my plan. In fact, my phone only times in 1, 3, 5, and 10. So we'll do 3 minutes. Ready, set, go. All right, if you draw ozone, which is O3, you end up with O with a double bond between another O and a single bond. All right? But you could also end up with a double bond to O and a single bond to O there. They're the exact same thing, right? Just on one of them, the double bond's on the other side than the other. All right? When this happens, we have what we call a resonant structure. So this is the structure we would see with O3. But this is at odds with the true observed structure of ozone, in which both O to O bonds are the same length. Well, that's kind of weird, because the slide, whether it's a single or a double bond, would affect how long the bond is. All right? And they found out they're equal. All right? So, it turns out that both outer oxygens have a charge of -1/2. Which is kind of screwy, but don't stress much about this. All right, we're just going to say that the double bond can be at the same time on both sides or at the same time on neither. It's just constantly flipping back and forth, essentially. And if you think about what electrons are doing, they're just spinning around nuclei, right? It would make sense that they might spin and be over there for a second, and they might spin and be over here for a second. And they're constantly flipping where they are. They're either on the left or the right side of the O. When this happens, we will draw it something like that. All right? One Lewis structure cannot accurately depict a molecule such as ozone. We use multiple structures, resonant structures, to describe the model. So we would draw both. Okay? Now, the only test question that I have ever given and ever seen in AP about a resonant structure is where it just gives you a couple things and it asks you which one would have a resonant structure. So to be able to do that, you just have to draw the resonant structures of the things they gave you. And if one of them has a double bond that could have been somewhere else, that's your resonant structure. If you remember, we did SO3. We had SOOO. This would have a resonant structure because we could have had S, O, O, and O. And where's the third one? All right, the double bond on the bottom. Those would be the three resonant structures of SO3. All right? What's that? You don't ever have to draw all three. It doesn't matter where it is. It just matters it could be in more than one place. So we draw, and I won't make you do it, but a true person would write all three of those resonant structures to show that it really is unknown. Okay, we're already past my time limit, but we'll be fine. So just as green is a synthesis of blue and yellow, ozone is a synthesis of these two structures. Okay? The key to this is what we call delocalized electrons, I think. Are they coming up? Yeah, there we go. The most common thing in our world that you may have heard of is benzene. Has anyone ever heard of that? It was super awesome, like cure-all thing back in the day until they found out that it kills people. Benzene's very toxic. But benzene has a bond here, a double bond here, here, and here. But we could just rotate those, right? And they could have been here, here, and here. So a benzene ring, they just draw a circle in the middle to show that it is a resonant structure. In truth, the electrons that form the second CO bond and the double bond between whatever below do not always sit between the C and the O, but they can move. All right? They are not localized, but rather delocalized. And this is a word you do need to add to your chemistry vocabulary. A delocalized electron is an electron that is free to move. And in this example, it's a pair of electrons that are free to move from one side of a molecule to another. So the organic compound, I knew that other slide fell out of order. Benzene has two resonant structures. It is commonly depicted as a hexagon with a circle inside to signify the delocalized electrons in the ring. Okay? So, the nutshell, electrons can move, and those would be pairs in this discussion. They're delocalized. And when there's more than one Val-Lewis structure that doesn't violate formal charges or anything, a better way to put that is where there can be a double or a triple bond in a different location, then you have a resonant structure. Okay. The next set is a lot more important than resonant structures were, and this is called exceptions to the octet rule. This should be like not a completely new section because it's still Lewis structures, but it's definitely an important thing. Now, will you quickly tell your lab partner what the octet rule is? All right. So it's when we put 8 dots around the central atom, essentially, in Lewis structure words. It's where the atom fills its valence electrons with 8, and life's good. So there are 3 main exceptions to the octet rule. All right. Here they are. They're listed, whatever. This one's the least important, and that's ions or molecules with an odd number of electrons. And we're going to go through each one of these. But if we have an odd number of electrons, then everything's going to be screwed up. We can't end with just 8 on everything. We had an odd number. All right. Ions or molecules with less than an octet. That's pretty rare. We're going to talk about that. All right. Ions are molecules with more than 8 valence electrons, and that is by far the most common and the one that you should make sure you understand. The reason here is we can expand an octet. We can go greater because now we have the D and the F shells that we can fill. All right? We typically don't go more than 10, but 10 is more than 8. So that's why we call it an exception to the octet rule. Now, put into your mind, we're going to go over each one of them individually pretty quickly. But they're important for your score. All right, so odd number of electrons, though relatively rare and usually quite unstable and reactive, there are ions and molecules with an odd number of electrons. So like nitrogen monoxide gas. Nitrogen has 5, oxygen has 6, so we add those up and we get 11 valence electrons. We put N and O next to each other, and then we combine them with one line. Okay, we put one line on them, and then we end up, first off, we want to octet oxygen. 1, 2, 3, 4, 5, 6. That would have 8. All right, and then I have 3 valence electrons left, correct? So I have 1, 2, and 3. But nitrogen only has 1, 2, 3, 4, 5. So it is best to get rid of a pair, form a double bond. Oxygen is still octeted, correct? All right. And then nitrogen now, it's closer to an octet, but it is definitely short. I end up, you can put it on the top or the bottom, it doesn't really matter. I end up with this structure, and the octet rule is not satisfied because I had an odd number. All right? Definitely more reactive, because if I just make this NO negative 1, life's a whole lot better, right? Now I have that. Now I have an octet on everything, and life's super more convenient. So nitrogen monoxide is out there looking for an electron constantly so that it can become NO minus 1 or NO2 or NO3 minus 1s. Okay, you okay with this? These are by far the most rare ones, but they're easy because if you just add them up and you have an odd number, well, you have an odd number, and you just make sure that the one that is short is the one that's less electronegative. Okay? If you have to screw one over, it's always going to be the one that's less electronegative. Okay, fewer than 8. This is by far this like exact example. It is tested on the AP test all the time. It's their favorite thing, is BF3. All right? So we have boron trifluoride. Giving boron a filled octet places a negative charge in the boron and a positive charge in the fluorine. This is just like we did, except for I did beryllium, but it's the exact same idea. This would not be an accurate picture of the distribution of electrons in BF3. So where did we get these numbers right here? It's their formal charges. All right? Boron cannot force fluorine to be positive. Can fluorine mess with boron? You bet it can. So what happens is fluorine just does what it feels like, and it leaves boron with an unfilled octet. You okay with that? Once we draw that model right there, whoops, there should be a line right here. Once we've drawn this, it's over. One of the dots didn't come. There's supposed to be another one right here. Whatever. That one should be there. That's ugly. But fluorine just takes the pair from boron because it's so much more electronegative. It forces boron to only have 6 out of the 8 in the octet. But it can. It's a bully because it's the most electronegative. Okay? So, therefore, structures that put a double bond between boron and fluorine are much less important than the one that leaves boron with only 6 valence electrons. And this goes to the boys' questions earlier. These things can certainly exist, but they won't for very long. And in percentage-wise, 99% of the time it would be boron with only 3 bonds and a non-full octet. All right? Who's okay with that? If you ever see that one, most likely it is BF3, and they're just trying to make you show them that you understand fluorine is so electronegative it can't force things to do anything else. Yes? It wouldn't technically be an ion yet, but it would be out there hunting for electrons to become one. All right, the lesson here is, if filling the octet on the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, don't fill the octet of the central atom. Okay? We're never going to have something left on the periodic table make something right on the periodic table become positive. That's just, it doesn't work that way. Okay, more than 8. More than 8's pretty simple. Especially here, PCl5. It has to have more than 8 around it because there's 5 things. All right, so the only way PCl5 can exist is if phosphorus has 10 electrons around it. It is allowed to expand the octet of atoms on the 3rd row or below. Presumably, d orbitals in these atoms participate in bonding. Okay, when you get more than 8, you have to know that that cannot happen until you're on the 3rd row or lower, because d shells don't exist till the 3rd level. All right? So, almost always, if you have a problem on this, it's going to be phosphorus or sulfur. And that, Jansen, that's why in those ones in that video you watched, he combined formal charges and this idea and put double bonds on some things. Okay? So, if you see a P or an S and then something in a big number, your exception is that you have a lot. Now, sometimes, and this is what Jansen had watched one of the ed puzzles. I put 2 on there if you wanted extra help on this. They're not required, but there's two good videos. All right, so now, PO4. Even though we can draw a Lewis structure for the phosphate ion that has only 8 electrons around the central phosphorus, the better structure puts a double bond between the phosphorus and one of the oxygens. So, this is valid, but this is the more correct. The reason why is because we've reduced the charges. There's only 3 total formal charges in this model, and there's no positive formal charge on the one on the right. Here, phosphorus was a +1. Okay? I know that's tricky. If you see P, that's an S. P and S, or S and P, there's a high likelihood you're going to be expanding your octet. It does that to satisfy either that there are more than 4 total things that it has to bond with, or to reduce the formal charges. Okay. Newman, was that a question? Okay. All right, this is what I just said. This eliminates the charge on the phosphorus and the charge on one of the oxygens. Here's the lesson. The lesson is, when the central atom is on the 3rd row or below, and expanding its octet eliminates some formal charges, you should do it. Now, there are thousands of these, but you're only going to see phosphorus or sulfur in this class. Okay? Check phosphorus, check sulfur. Those are your red flags. All right? Okay. The rest of the hour, I want you to draw these 5 Lewis structures for practice.